All right, today we're tackling the fundamental language of energy itself, thermodynamics. It's the science that connects something as huge as a power plant to the refrigerator sitting in your kitchen. And to really get it, we've got to start with the core vocabulary.
So, think about this for a second. What could a steaming cup of coffee, the engine roaring in your car, and a high-speed aircraft possibly have in common? Well, the answer is all about energy, specifically how it moves and how it transforms. And the science that gives us the rulebook for all of that? Yep, that's thermodynamics. Okay, so let's jump right in and start building our foundation. First things first, we've got to get a really solid handle on what thermodynamics actually is before we can even think about putting it to work. The best way to think about this is like learning a brand new language. And the source material really hits the nail on the head here. To build anything meaningful, you need a solid foundation, right? For us, that foundation is getting the basic vocabulary down cold. So let's get to the heart of it. What is thermodynamics? Well, at its core, it's the science of energy. The name itself is a dead giveaway. It comes from the Greek words for heat, which is therm, and power, which is dynamis. That tells you a lot about its origins, which was all about figuring out how to turn heat into useful work. It's basically the rulebook for how energy makes things happen in the universe. All right, so the very first word in our new language, our first piece of vocabulary, is the system. It's a simple idea, but it's so important. Before we can even start to analyze how energy moves around, we have to be super clear about what exactly we're looking at.
Think of these as the fundamental nouns of thermodynamics. The system, that's our main character, the thing we've decided to study. Then you've got the surroundings, which is, well, it's literally everything else in the universe. And separating the two is the boundary. This can be a real physical thing or just an imaginary line we draw. I know it sounds basic, but trust me, getting this right from the start is absolutely crucial.
Okay, so systems basically come in two main flavors, and the difference between them is super simple. Can stuff get in or out? That's it. On one hand, you have a closed system. Here, the amount of mass is totally fixed. Energy, like heat, can get in and out, but the actual matter is stuck inside. On the other hand, you have an open system. With these, both mass and energy can cross that boundary.
So for a closed system, the classic example you'll always see is a piston cylinder device. Just picture it. You've got some gas trapped inside. That amount of gas is fixed. We call that our control mass. Now the piston can move, right? It can go up and down, changing the volume, letting energy in or out, but the gas itself, it's not going anywhere.
And for an open system, just think of anything where stuff flows through it. Your water heater at home is a perfect example. Cold water comes in, hot water goes out. A jet engine is another one. Air gets sucked in the front, hot exhaust blasts out the back. In these cases, we call the system a control volume because we're not focused on a fixed piece of matter, but on a fixed region in space that stuff is moving through.
So you might be wondering, why do we even care about this distinction? What does it matter? Well, it's because you simply cannot solve an energy problem until you've defined your battlefield. Deciding whether you're dealing with a closed system, like that piston, or an open system, like a turbine, is the absolute first step, and it dictates every single calculation you're going to make after that. Okay, so if the system is our noun, we now need some adjectives to describe it. In thermodynamics, we call those properties. These are the words that tell us about the condition of our system.
And a property is really just any characteristic of that system that you can measure, observe. I mean, we're all super familiar with these already, right? Things like temperature, pressure, volume, mass, they're the specs, the details that describe what's going on. But, and this is a really key distinction, these properties fall into two main camps. You've got intensive properties. These are things that don't care about the size of the system. Think temperature or pressure. And then you have extensive properties, which absolutely depend on the size or amount of stuff you have, like the total mass or the total volume.
Okay, so how can you easily tell them apart if you're ever stuck? Well, there's a really neat little thought experiment that makes it super clear. It's called the division test. Just imagine you have a system, let's say a room full of air, and it's all uniform. Now, in your mind, just slice it right down the middle into two equal halves. Ask yourself, what changed? The temperature in each half is still the exact same as the original room, right? That makes temperature intensive. But what about the volume? Well, the volume of each half is now 50% of what it was. That makes volume extensive. See? It's a foolproof way to figure it out.
All right, so just to recap, we've got our noun, which is the system, and we've got our adjectives, which are its properties. When you put them all together, they give us the system's state.
And a state is just its specific condition at one single moment in time.
Yeah, think of a state as a snapshot. At that one instant, every single one of its properties has a fixed, specific value. And if you change just one of those properties, like you crank up the pressure, boom, you've just pushed the system into a brand new state. A huge part of thermodynamics is studying these states, especially the really stable ones, the ones that are in balance. We call that equilibrium. So a system is in thermodynamic equilibrium when it's basically at rest. Nothing is changing. And for that to happen, it needs to be in total balance in a few different ways. It needs thermal equilibrium, the temperature is the same everywhere. It needs mechanical equilibrium, no pressure differences. And it needs phase and chemical equilibrium, meaning its physical form and chemical makeup aren't changing either. It's a state of perfect, unshakable stability. Now, this brings us to something incredibly useful called the state postulate. Think of it as a powerful shortcut, almost like a cheat code for thermodynamics. It tells us that for a simple system, you don't need to know a long list of properties to define its state. You just need two. If you know two independent, intensive properties, say, the temperature and the specific volume, you can calculate everything else. This is a huge, huge deal for engineers. It saves so much time and effort. Okay, so far, everything we've talked about has been pretty static, right? We've been describing these frozen moments in time. But the real magic, the whole point of thermodynamics, is understanding change. And that brings us to the verbs of our new language, processes.
A process is really simple. It's any change that moves the system from one equilibrium state to another. The journey it takes, that series of states it goes through, we call the path. And if you have a bunch of processes that eventually bring the system right back to where it started, you've just completed a cycle. This is literally what's happening over and over and over again inside your car's engine.
Now look, in the real world, change is often fast, messy, and pretty chaotic. That makes it incredibly hard to analyze. So to get around this, engineers use a very clever idealization called a quasi-equilibrium process. The idea is to imagine the process happening so incredibly slowly that the system is always in balance, always in equilibrium. So imagine compressing a gas one molecule at a time. Of course, this isn't how things actually work, but it gives us a perfect idealized benchmark, a 100% efficient process that we can compare all our real-world devices against. Okay, so let's do a quick recap of the language we've just learned. The system, that's our noun, the thing we're studying. Properties, those are the adjectives that describe it. State, that's its condition at a single moment. And process, that's our verb, the action that causes change. With just these four basic concepts, we can start to tell pretty much any story about energy. So, we've got the basic grammar down. The real question now is, what do we do with it? How can we take this language and use it to analyze efficiency, to design better engines, to understand the flow of energy that powers our entire world? How can we use it to build a better future? That right there is the true power of understanding the language of energy.